Hello, I hope you're doing well after the crazy weather last week in Texas. So, hopefully, everybody's safe and healthy. So, today I'm going to continue with the course and start a new topic, which is kind of related to what we saw um, on time independent perturbation theory. And it means to apply these techniques for the study of the hydrogen atom. So, we're going to review concepts such as fine structure, spin orbit coupling, and the hyperfine structure. So let me share my screen. Okay. So basically, we will use time-independent perturbation theory to introduce some corrections of additional effects over the hydrogen atom beyond what you studied on your previous quantum mechanics course. And yeah, I mean, they're basically the fine structure that's made of a relativistic correction and a spin orbit coupling, and then the hyperfine structure. So there are some preliminaries that I want to mention before we start, um, which is the following. I mean, I'm going to study for ex example purposes the hydrogen atom, but these can also be extended to basically so-called hydrogenic atoms, which are hydrogen-like in the sense that they have an electron in the last layer. And so, as you know from your previous course, the potential of the unperturbed hydrogen atom is a Coulomb potential, which has 1 over r dependence, and c is the atomic number, so the number of protons in the nucleus. And in the hydrogenic atoms, there is an electron interacting with the nucleus. For the simplest case we're going to study, which is the hydrogen atom where the nucleus is only 1 proton, which is one of the possible isotopes of hydrogen. Um, what is convenient to do is to basically switch coordinates to the center of mass and the displacement vector between the electron and the nucleus. So if you do that change of coordinates, as you probably know from classical mechanics when you study, say, two-body problems, and possibly you have seen this before in your quantum mechanics 1 course as well. So the position of the center of mass is given by this weighted formula relating the masses and the positions. Then there is another concept of the so-called reduced mass, which or whose inverse is obtained by the sum of the inverses of the masses. And this gives the following formula for the reduced mass in this context. And if you basically do this change of coordinates, what you'll find is that the Schrodinger equation related to the center of mass is something like a free particle, um, or Schrodinger equation free particle. So this is indicating that the center of mass is moving, say, at a given constant speed without a potential affecting it. And then if you look at the relative motion, basically, or the coordinate, that is this displacement vector between the electron and the nucleus, that's where you have uh, the problem as you had for the hydrogen atom unperturbed, with the only difference that you have to use the reduced mass and this displacement vector between electron and nucleus. Anyways, I mean, the reduced mass in this situation is actually close to the value of the electron because the mass of the proton is around 1,836 times the electron mass. So if you do the calculation by means of the formula above, and you divide conveniently by the proton mass above and below, you'll get this value. I mean, this is pretty close to ME. And again, this is the coordinate that we're going to use, and we're going to refer it as R in our situation. And we're going to assume that we have done the change of coordinate needed and use of reduced mass, etc. So again, we have done this replacement, and in the right coordinates just indicated the Hamiltonian for the unperturbed hydrogen atom, which is what you studied before. And let's put, for example purposes, C, the atomic number equal to 1, is the Bohr Hamiltonian, where you have the kinetic energy term and the potential 1 over r term, right? So this is your old friend um, on the hydrogen atom Hamiltonian. So we're going to build on that to make some observations. And the first one is the study of the fine structure. So again, a fine structure is a correction appearing in the Hamiltonian for the hydrogen atom, where two additional effects must be considered. So one of them is the effect of relativistic corrections to the kinetic energy operator. And the second is a phenomena called the spin orbit coupling. So this perturbation is basically an order alpha squared lower than the perturbed Bohr hydrogen atom Hamiltonian. And alpha is a so-called fine structure constant, which is made of these parameters and is around 1 over 137. And so basically, I'm saying that our effects in the perturbation are going to be lower by alpha squared because the Bohr energy is of order alpha squared mc squared, and the fine structure corrections are going to be of the order alpha fourth mc squared. So let's study each effect separately, and then we'll add their contributions. So regarding the relativistic correction, so far the kinetic energy operator that we have used in quantum mechanics, of course, has come from classical physics. So it's p squared over 2m, where p is minus IH bar nabla, right? So, of course, this is the classical term, but we know from special relativity that the kinetic energy, if you, of course, take out the rest energy of bodies, is actually given by this formula. So this is, of course, the rest energy. And by taking the difference, we have the kinetic energy that is related to the movement or the motion of the object, right? So we have the B over C squared, which of course appears in relativity problems. And so we want to propose a new kinetic energy operator that considers this relativistic correction. In fact, we're going to use an approximate term, and I will explain in a second how it's obtained. So this is going to correct the classical approximation. And in order to get an appropriate operator, first what we're going to do is to express the kinetic energy in terms of the relativistic momentum. So the relativistic momentum looks like this, is basically the classical momentum divided by the square root of 1 minus b over c squared. So you probably have seen this in a special relativity course or modern physics course. And if you have this computation of basically p squared c squared plus m squared c the fourth, what you can obtain is that this is equal to the square of the kinetic energy over here, this difference. Uh, well, actually, in total, right? Because I passed to this other side. So that's the total kinetic energy um, to the squared power. So we're just doing this computation because I want kinetic energy in terms of the relativistic momentum. And this is the formula that I achieved here. And of course, taking the difference to eliminate the contribution of the rest energy. So, of course, well, we're going to introduce this relativistic correction, and we know that in the limit, say b over c goes to 0, or equivalently, p over mc, if you do this computation, goes to 0. The relativistic case approaches the classical case. And so we expect the same for the operators we propose. So, I mean, we're interested in this limit, but of course, to obtain some sort of first order correction, right? And so, I mean, basically, if we do this kinetic energy relativistic in terms of the relativistic momentum as basically a series expansion related to the square root, and you obtain a series of terms, the first term will be the classical contribution, which in the limit is basically to what this operator approaches. And the second term will be like the first meaningful relativistic correction to the classical case. So that's exactly what we're going to do. So what you can do is basically factorize this MC squared. Uh, if you do that, this is the form of the square root. And then what you'll do is to expand the square root around 1 using a Taylor series. If you do that, of course, your first term is 1, then you have the expansion of the square root of this object. And you have to remember that after you factorize, basically you have to take a you have to take a difference minus 1 over here. So this term will go, which makes sense. And further on, if you multiply by MC squared outside, well, this is the first term coming from this expansion, then the second term, etc. And if you clean up a little bit your computation by performing these computations with the MC squared, what you get is, of course, the classical term, which is the first term when you do this limit as P over MC goes to 0. And then the first order somehow relativistic correction, right? I mean, in a way, I mean, this is not exactly the parameter we're using, but in this limit, what is going to 0 is P over MC or B over C. Um, so again, this is the kinetic energy that we know from the classical case, which happens in the classical limit. And the second is a relativistic correction, and it's the lowest order one we can do, right? So if we want to introduce relativistic corrections, basically what we're going to do is to consider that this is a correction to the kinetic energy, not to the potential, as we had seen before, but still it's a correction to the Hamiltonian. And so this is the perturbation Hamiltonian that we will consider regarding relativistic corrections. So it depends to the fourth power of P and divided by some constants. And well, we will use this perturbation Hamiltonian to calculate the corrections coming from this contribution. Now, there's, in principle, we know that the hydrogen atom beyond the ground state is degenerate. However, there is a justification in this particular case to use basically the non-degenerate formula for the first order energy corrections. And I will bring the justification in a second. I just want to do the computation first, but for the moment, just believe me, and then I'll give you the reasons you can perform the computation for the first order corrections as if you were in the non-degenerate case. So if we were to use that formula, of course, we had to justify it. But again, the formula is to calculate the perturbation Hamiltonian averaged over the unperturbed states, which are coming from the Bohr hydrogen atom. And well, we can take out the constants. Then basically we can use the hermiticity properties of this operator, passing a p squared. And so this is basically the norm of the p squared psi NLM state. So we just have to figure out where this operator is shifting it, right? Now, we're going to remember a little bit of what we learned regarding the hydrogen atom in your previous course. So when it's unperturbed, well, we have the kinetic energy in the classical case, of course, the potential of the hydrogen atom, and then the energy eigenvalues, which are the Bohr energies. And if we do some simple algebra, we basically pass the b to the other side and the constants 2m, etc. And we have that the effect of p squared over the wave functions, and here I'm having a typo, is basically 2m times the energy eigenvalues in the unperturbed hydrogen atom minus b, where b is the Coulomb potential. So we can do that calculation of the first order correction, which of course we have to justify. Just wait for me 1 second. And well, we know that p squared acts over psi with this effect. So we simply substitute with this operator. And then we again go back using hermeticity to this operator, excuse me, E naught n minus b squared. And this is more treatable. I mean, you can expand the square of this operator, especially because this one is constant, just the eigenvalues, and do the calculations. And if you expand in the square and then compute, you get the square of this constant minus 2 the energy eigenvalue average of the potential, and then basically the computation of the average of b squared. So so far we have done in general, but we have to plug in the potential we're using, right? Which is of course the Coulomb potential with c equal to 1. And so if we do that, we basically need to know the average values of 1 over r and 1 over r squared over the uh, wave functions. So, I mean, you can prove that the result of the average of 1 over r is the inverse of n squared a, where a is the Bohr radius. And for the case of the inverse of r squared, we have this result. So, yeah, I mean, it's of course order a squared, since this is r to the minus 2. So this is a squared to the minus 1. Then you have n cubed, and it also depends on the quantum number L. So we would plug in these results over here. And then what we would also do is, well, we're starting to get the quantum numbers N and L appearing, right? And these energies of the hydrogen atom have also a dependence on N. So, well, more additionally, we have the formula for the Bohr radius, which is A. So if we plug in all these results, so in this factorization, of course, this is showing the 1 over n squared dependence on uh, the hydrogen atom energies. This is basically the energy for the case n equal 1, which would be the ground state of hydrogen. And then once you plug it in, you can reduce this formula into this. Of course, there will be some elimination coming up and so on. But okay, this is telling you that the relativistic correction to first order, which I have to justify because it's a degenerate situation for n greater than 1, is depending on the square of the unperturbed energies divided by 2mc squared. Notice this. So you have the basically rest energy of Einstein appearing over here, and then this dependence on the quantum numbers. So, okay, the important part, because at the end of the day, this is a computation, is why are we justified to use the non-degenerate formula, right? So what happens is that the perturbation is spherically symmetric, and it commutes with the angular momentum operator L squared and the C component of L. So if you remember your study of the unperturbed hydrogen atom, with these two operators, you can essentially generate the spherical harmonics by using them as ladder operators. And this does not happen only for the hydrogen atom, but in general for central potential, for which the Coulomb potential is a given example. So, okay, basically our perturbation Hamiltonian commutes with these two. And so the eigenfunctions of these operators, if you consider them, well, and then you also consider basically the calculation of the energies to first order, well, they have distinct eigenvalues that depend on the quantum numbers n comma L. So if you remember, basically for the level n of energy in the hydrogen atom, there is an n squared degeneracy. So of course, for the ground state, it's not degenerate, but for n 2 and greater, it is. And n squared is the order of the degeneracy. But basically, what is happening is that, well, if you have, you are in this degenerate subspace, of course, the they all have the old energy E0n, but with different tail, these values are different. And basically, this is related to diagonalizing the perturbation Hamiltonian in the degenerate subspace. So there is a way to distinguish it. And this is the situation we expected from the theorem we stated last time, where basically you would find operators that commuted with the Hamiltonian and the perturbation, which is what we're proposing. And then in that case, essentially what you can do is to consider that the perturbation is breaking the degeneracy in a way. Not all, but part of it. So this is the second point that I want to make. So in a way, the old eigenfunctions were the good states, because these unperturbed states, or from the unperturbed Hamiltonian, they are simultaneously eigenfunctions of the old Hamiltonian of L squared and LC. And we can use the non-degenerate perturbation theory in the way or in the spirit of the theorem, where you find an operator that commutes, etc., etc. But the other comment that I wanted to make is that, well, this first order correction related to the relativistic correction, if you notice, the quantum numbers appearing are N and L. So in principle, the degeneracy in L has been broken by this perturbation, this relativistic correction. But M is not appearing. So there is still a 2L plus 1 degeneracy in M. Say, basically what this is telling you is that if you choose, of course, in the degenerate subspace, all the states have the same N, right? But if you choose different tails, they will have different energy, and then the degeneracy has been broken, and the states were um, semi-diagonalized in a way. But if you choose the same L and different M, in principle, they are different states. They have different quantum numbers, and their energies are still the same, because M is not appearing here. So up to a point, we have broken degeneracy as far as N and L are regarded, but not in N. And this is related to the fact that this is related to rotational symmetry. And the perturbation to the kinetic energy made by the relativistic correction doesn't break it. So in a summary, well, this is the relativistic correction, which has come from basically the correction to the kinetic energy, and then a justification to use the non-degenerate formula in this highly degenerate case, which is the hydrogen atom. And so this is only one of the two effects related to the fine structure. So the second mm, is related to the spin orbit coupling. And excuse me, I just took a cup of water. So the other effect, again, that is contributing to the fine structure correction is this coupling of spin orbit coupling, so-called. And what happens is that, well, let's imagine that you are the electron, and from the point of view of the electron, it is observing that the proton is circling around it. Now, I know that this system is non-inertial, so there is a way to correct for it, which I'll tell in a second. But for the moment, let me sit in the point of view of the electron, in this non-inertial frame of reference of the electron, the hydrogen atom. So because the proton is orbiting around myself as an electron, this positive charge generates a magnetic field, just as in the figure, right? And so this magnetic field exerts a torque on the electron because it has a spin. So it's in this caricature picture in the classical case is spinning, although that's not the correct quantum picture of it. So what happens is that there's an alignment in magnetic moment along the direction of the magnetic field. And we know from classical physics the Hamiltonian related to this interaction. So this is minus mu times b, where where mu is a magnetic moment and b is the magnetic field generated. And so we need to calculate this in order to have a quantitative measure of the perturbation Hamiltonian. So of course, this is a caricature picture. This is the hydrogen atom from the perspective of the electron. So the electron is sitting in the center in this non-inertial frame of reference. It sees the proton orbiting around, and this is the direction of the magnetic field, and also the oscillator of the angular momentum. So, well, after a picture has been presented, um, so if we consider the magnetic field generated by the proton, uh, so the proton is describing a loop, and of course, the current that is related to this orbiting or this circling is the charge of the proton, which is plus E, divided by the period, right? And so we can use the Biot-Savart law to calculate the magnetic field related to this uh, movement. So we have mu naught I, the current, and then divided by 2r, where r is, of course, the radius of this circling movement. And so B, it turns out it also points in the same direction as the orbital angular momentum of the electron in our, well, in the inertial frame of the nucleus. And if we use Ampere's law to figure this out, basically, well, we'll have this proportionality relation where, of course, we have the angular momentum because we have r cross b by some constant. So we have EL divided by some proportionality constants. And so what we have done so far is basically calculate the magnetic field generated by the proton. So what about the magnetic dipole moment of the electron, right? So as we mentioned, the interaction is due to this alignment of moments where the electron has spin. And well, the proportionality relation between the magnetic dipole moment of the electron and the spin uh, has a proportionality constant, which is called the gyromagnetic ratio. So I'm not going to present the classical calculation, which is in Griffiths if you want to check it, because actually it has to be corrected. So, I mean, of course, it's a nice exercise. If you are curious to check it, please feel free to do it. But it has to be corrected anyways, and it's off by a factor of 2 from the quantum value. And in order to explain this difference and this correction, you need to consider the electron relativistically. So for the moment, just believe me. I think the classical calculation would just give you a taste or a flavor, but it's not complete, and you probably have seen it on your electromagnetics course, anyways, um, possibly, uh, if you went into charging spheres, etc. So in any case, the magnetic dipole moment of the electron, okay, is proportional to the spin. You have the charge of the electron and then divided by m. So there is a factor of 2, again introduced as a correction. So this is the final form in the quantum case. And now that we know B, the magnetic field generated by the proton in this non-inertial frame, and then the magnetic dipole of the electron, we can simply plug in the formula for the perturbation Hamiltonian over here and do some calculations, right? So what we are going to have essentially is a dot product of the spin of the electron with the orbital angular momentum of the electron as well. And okay, some constants will go out, etc., etc. You can factorize them, but this is a situation, and of course you have some dependence on the radius of the circling orbit, right? So this is the one for r cubed that is appearing in this case. Yeah, although it's constant in the in in the movement for the classical picture. Now, the $1,000,000 question is, of course, what you have been thinking at this point. Am I justified to use a non-inertial frame of reference in my calculations by sitting on the electron? Not in principle, but you can correct for this non-inertial frame by introducing a kinematic correction, which is relativistic, and that is called the Thomas precession. So we're not going to justify it, we're going to use the result. And so it basically amounts to a factor of 1/2. And actually, the factor is related to the correction of the magnetic field value. So just FYI. And then in that case, we have to introduce that factor to basically go from the non-inertial frame result to the inertial frame one. And if we divide by 1/2, the formula above, we have 1/8 instead of 1/4 for the spin-orbit interaction. So basically what is happening is that there is this, again, interaction of the magnetic field generated by the proton in this frame with the electron spin. So this is due to the orbiting of the electron and its own spin, right? So that's why it's called the spin-orbit interaction. And so it's proportional, this Hamiltonian, to the dot product between the spin and the angular momentum of the electron. So what happens is that now we're considering two angular momentums, right? So in this spin-orbit coupling, Hamiltonian by itself does not commute with the orbital angular momentum L and the spin S only. So what you have to do is to consider basically the total angular momentum. So this will be the good momentum to consider. So not individually this one or this one, but the sum of these two. And this one will be conserved actually. And also what will be conserved will be basically L squared and S squared. So perhaps not the vector quantities are conserved, but this spin orbit Hamiltonian commutes with these operators, L squared, S squared, and J, which is the total momentum. And these are going to be conserved quantities. And this is giving you a hint into basically the good states that you have to consider, right? So what you have to do now is to use the eigenstates of L squared, S squared, J squared, and JC. Notice this is as when you had basically a single angular momentum, L. So this technique still holds as the good states. So, I mean, you cannot keep using LC and SC as a guideline for your good quantum numbers or your good states. And actually, the formula for the dot product is easy to derive if you consider that this is the total angular momentum. If I calculate J squared, this is basically, uh, I mean, obtained by the dot product of J dot J, where you plug in the formula for J. And then if you perform the dot product, you get this. So basically, by separating L dot S and dividing by 2, then you have this formula. So the dot product of S and L is J squared minus L squared minus S squared divided by 2. And as you could expect, basically this operator has eigenvalues proportional to h squared over 2, of course, but it's related to quantum numbers J times J plus 1 minus L times L plus 1 minus S times S plus 1. And for the spin, in case of the electron, of course, you already know that S, its spin is 1/2. So if you do the computation S times S plus 1, it is 3/4. So that is fixed. And well, um, so we have covered part of the terms in the perturbing Hamiltonian. But if you were again in the same justification grounds to basically calculate the first order correction related to spin orbit interaction, you have that the average of H prime spin orbit, uh, well, the constants will come out, of course. What is dependent on uh, state and the integrals over the space you're performing are S dot L and R cubed. You'll have to believe me at this point that the result of this calculation is related to basically the ratio of these functions of quantum numbers. And you can clean up a little bit the calculation. You would think that there is a singularity for the case of L equal to 0. Physically, in that situation, there wouldn't be spin orbit coupling. And anyways, when we add the contribution of this spin orbit coupling with the relativistic correction, the singularity will disappear, so don't worry too much about it. And again, we have the formulas for the Bohr radius and then also for the unperturbed hydrogen energies. And that is because we'll get like some 1 over n squared dependencies. So if I clean up a little bit my basically formulas over here, and of course I'll have the Bohr hydrogen energies to the squared with this factor of n divided by mc squared, which was popping up over here related to these factors, and then this function of quantum numbers. So this is the short summary for the spin orbit coupling. Clearly there is some coupling of angular momentum, the L momentum with the S spin. So we have commented quickly on the basically with quantum numbers to use, etc. But what is interesting is that if you compare the formula that you just obtained, think about it, right? Okay, we have this dependence on quantum numbers, but this is basically, well, this is proportional to the square of the unperturbed energies divided by mc squared. And the same factor actually appears when you remember what we obtained for the relativistic correction to the kinetic energy. So we also have a factor of like that. Of course, we have a different function of quantum numbers. There's a factor of 1/2, but roughly they are, let's say, of the same order. So that is nice, first of all. Second, that indicates what we have to add them because they are of the same order. And so they are both important and you cannot disregard one versus the other when considering the corrections to the hydrogen atom. So again, this is in a way the order of the energy, and we need to add them to get the fine structure correction. So it is made, this correction is made of the spin orbit coupling and the relativistic correction. If we do that, we basically factorize by this common factor. We have this contribution, then this other one. The factor of 2 in this case is justifying or justified because of this. And well, the other thing is basically that we have to do the computation. So, well, one thing to notice is that this term particularly, okay, in the numerator you have L and L plus 1, and in the denominator you have L, L plus 1, and L plus 1/2, and well, multiply by n. And this one is kind of the same fashion, right? I mean, what I'm trying to tell you is that if I separated this one from this bracket and I did it with this one, this other one, I would get some cancellation because they're very similar. So it's actually easier to simply introduce this term in here, which you can perform. So this is basically why the 3L times L plus 1 appears um, by adding this in this part. And then you have the tree. So, well, so far it looks like a long formula, but you have to use another fact, which is actually part of the hint in a problem of Griffiths. So I have done half of the problem for you in the lecture notes, and I'll leave you the second half, which is, um, well, less work, especially because I have showed you how to do the computation in this part. Mm, by using the fact that the quantum number j is equal to L plus minus S. And with S being equal to 1/2, right? So J is equal to L plus minus 1/2, except for the case L equal to 0, where you only have the positive sign. And in that case, J is equal to 1/2 solely. So I'm going to do the case of the plus for you in this variation. I'll leave you the minus for you to do. And if you do that, basically you have to plug in over here in the numerator. There will be some cancellation happening. And in fact, what you have to do is to basically separate by squares and expand, essentially. So yeah, I mean, what you could do is to simply multiply this one with this one, then you'll have the square, then you expand, then this one comes cleanly because it's L plus 1/2 times 1. Then you do some cancellation with this one, with this minus 3L squared minus 3L. Then you'll have the 3/4. And well, if you do the gathering of the terms and subtractions, basically you get this clean form of this term. So that's pretty neat. It can be, of course, further factorized if you factorize by L, and if you want even the factor of 2, which will give rise to the L plus 1 half, which is convenient because I have L plus 1 half below. So that will die, and also uh, the L in a way. So that's also a reduction. And well, so these two terms will go. I'll just have minus 4n divided by L plus 1, which is equal to J plus 1 half from this formula for the plus case, of course. And this looks quite clean. So again, this is the calculation for the case where J is equal to L plus 1 half. So I'll leave you the case of J equal to L minus 1 half, which is not, or which excludes the case L equal to 0 for you to do in the homework. So it's similar in this fashion. So, well, basically by adding the spin orbit coupling correction and the relativistic correction for the energies, you get the fine structure by this formula. You can also polish it a little bit. Well, no, this is polished in terms of the correction. What you can do is add it to the unperturbed energies to get the formula for the energy up to first order, right? Because it's the 0th order plus the first order correction. So we're going to use this for some factorization. And again, remembering also the defined structure constant is made of these terms and is of the order 1 over 137. And again, my point, right? So what is the energy up to first order? The unperturbed energy, which is the 0th order plus the first order correction. So this is, of course, an approximation, and it's up to first order, but it's what we have. So it's the first order correction plus the old energy. And well, I mean, I noticed that the fine structure correction has at least a factor of E0n. So I can factorize. So this is coming cleanly. And then what I will do is to simply substitute the formula for the unperturbed energies of the hydrogen atom, where this is the Rydberg constant. For n equal to 1, I have basically the energy in the case of the ground state. Um, and so, which is why this is in electron volts. And then if I further do some manipulations by using the fine structure constant, alpha, basically, well, I can put this, okay, so I have my um, Bohr hydrogen energy as a factor outside, and then I have 1 over alpha squared divided by n squared, and then this factor. So this factor is inherited from this part. And well, so one last thing to comment is that degeneracy in L is equal to J minus plus 1 half has been broken, because not all values of L carry the same energy when you consider E depending on N and J. But basically, the degeneracy in J has been kept. And the simple way to see it is that, well, this energy depends on the quantum numbers N and J, right? So you might have the case of the same, basically, NJ with different L if you want to figure out your way, especially with the plus minus in this case. And they will have the same energy. So basically, there are some states where not all the quantum numbers are the same, yet they have the same energy up to first order. So the degeneracy has been broken partially up to first order. One last thing to point out is the quantum numbers for the good states for the fine structure problem are basically n, okay, that you would expect because it's defining the energy, L, S, J, and only the Mj, which is related to the C component of the total angular momentum, right? So this also gives you more to think about the degeneracy in J with these other possibly different quantum numbers, right? The LS and MJ. So I'm not going to show the picture of the basically fine structure correction to the energy levels. I'll let you to check on Griffiths. Please do it for completeness. And so what I'm going to finalize the lecture with is basically with the hyperfine energy correction. And so this is of a lower order than the fine structure. Um, I mean, the reason you have these names like fine structure, hyperfine structure, well, and of course, these are variation in the energy levels that appear in the spectroscopic measurements, right? But specifically about this finer or hyperfine energy correction, um, well, it is due to the interaction between the magnetic dipole moments of the electron and the proton. So what we considered before in the spin orbit coupling was basically the interaction between the spin of the electron and the magnetic field due to the orbiting, right? In whichever frame you want to think about it. But now, I mean, in addition to the orbiting, we know that also the proton has a spin. And so you have two particles with the spin, the electron and the proton, and there will be some interaction related to this fact. And therefore, you have to calculate the Hamiltonian to introduce as a correction as it perturbs the previous considerations. So, well, the magnetic dipole moment of the proton has this formula. So this is the formula that you would have in any case. So this is the charge of the particle divided by 2mp, then the spin, and this is the dipole moment. So it's proportional to the spin. And then this factor is called G factor. I think it's called Landis G factor. And for the case of the electron, we had already made uh, considerations about it. So for basically the electron, this G factor would be 2. And so it would cancel with these two that would appear in the general formula, and that's why we don't have it, right? So this is this so-called quantum correction to the classical calculation. So in the case of the proton, though, this G factor is basically around the value of 5.59. And of course, basically the proportionality between the magnetic dipole moment and the spin is called the gyromagnetic ratio in TOTHE. And for the electron, we have already mentioned it. So, okay, this is covered for this moment. And so the magnetic field associated to the dipole in classical electrodynamics is given by this formula, right? So we're going to use the classical term extended as a quantum operator. So this magnetic field, okay, has some constants, 1 over r cubed. Then you have basically a projection of mu with respect to r, or in the direction of r. So that's the r component taken out of mu with a factor of 3 over here. And then you have a Dirac delta in this case. So that's something to consider. So, well, we know that the interactions of this type related to basically magnetic fields generated by these dipoles, which in this case is a spin, are given by basically minus mu times b. Now, in this case, the mu is the magnetic dipole of the electron, and b is related to the magnetic field generated by the proton in the inertial frame due to spin. So that's why on one hand, you're going to have the spin of the electron related to mu e by the proportionality on this Euromagnetic ratio mindset. And then you're going to have the spin of the proton in this case, right? Because this magnetic field is related to the dipole or the magnetic dipole moment of the proton, and it appears here. So, well, I mean, the first part is, of course, plugging in the formulas. So you have mu e, so proportional to the spin of the electron. This invokes the classical formula, where, of course, you're going to go from the classical term to the quantum operator. So it uses the magnetic dipole moment of the proton, substituting where needed. Then you use this proportionality relation for the magnetic field dipole. Sorry, I got distracted by it. I apologize. Of the proton. And then, well, what will happen is that you will have to perform this inner product, right, between spins. So, well, I mean, actually, you will have an R over here. I mean, the proportionality constants will go out, of course. You'll have a 1 over R cubed dividing, in this case, for this term. Then you'll have SE, or spin of electron, dot product, the R, and so on and so on. And, well, you'll have this term, what matters, and then with some proportionality constants, and then this term with the Dirac delta. So again, on this justification to perform a non-degenerate formula type in the degenerate space that I gave before, we calculate the first order correction to the energies by perturbation theory. And so this is equal to the average over the unperturbed states of the perturbation under consideration. So it's the average of this term. Of course, the constants have come out, so they don't matter too much. And then plus this other term, which involves SE dot SP with the Dirac delta. Um, Too many emails, I always. Yeah, it never stops, never mind. So, well, you have to perform these two calculations, right? Now, well, the spins are going to be independent of the integral over position space. So you can somehow, like, basically divide them in some sort of Fubini's theorem. So you'll have the average of this quantity. And this integral is going to be related only to the position part. And so the role of the Dirac delta function will be to localize around zero. So that's why you have the wave function normed squared at zero. So this is the justification for this part. For this other, the term is more involved. So actually, what we're going to do is to simply consider a simple case, which are states where the angular momentum number L is equal to zero. And you can prove, and this is going to be the second problem of the homework, that the first expectation value is zero. So in this case, L equal to zero, we can disregard it, and it won't be considered anymore for this case. Now, if we further restrict ourselves to not only L equal to zero, but to basically the unperturbed ground state, so basically we're in the situation of quantum numbers 1, 0, 0, and we can plug in the value of this probability density, which is 1 over pi a cubed. So what we'll have in that case is simply plugging in this value, is that we need to consider the average of SE dot SP. So, I mean, it's not surprising that the effect is called spin coupling, because basically the perturbation is appearing by the interaction of the spins of the electrons and the proton. It also shows up in the formula when you have to compute this dot product. And well, the same consideration that we had before, where each of the individual spins is not considered, but not conserved, but what is conserved is the sum. You have to do the same way of thinking, right? So basically, the good states are going to be related to the total spin S, which is the sum of the spin of the electron and the proton. And so we'll have the S squared operator appearing, which is S dot S. And we're going to obtain again, excuse me, the dot product of E dot SP by this relation, by popping or plugging in the terms and then popping up with this one. So we have a similar formula, right? So this is this dot product is equal to the total squared minus the individual contributions of each one divided by a factor of 2. And then, well, the electron and the proton are fermions of half integer spin 1/2 that you already know. So you can calculate separately some of these terms, right? So regarding SE squared for the electron, this is 1/2 times 1/2 plus 1 times h bar squared. So this is 3h bar squared over 4. And the same for s squared for the proton. Now, there can be two possibilities, right? When the spins of the particles are parallel, and the name for this is the triplet state. And then the total spin is 1 because they add up, right? So 1/2 plus 1/2 equal to 1. And in that case, for s squared, what you'll have is 1 times 1 plus 1, which gives you 2. So on the other case, where basically you have the anti-alignment, so in the singlet state, the total spin is 0, because you have the 1/2 minus 1/2. In that case, so s squared is 0. So, um, well, in that case, you can consider the two scenarios in the formula for the values of s squared. And well, these are constant and they are the same for these two. So it will be double this quantity when you add these two together. So for the case of the triplet state, where basically s squared is equal to 2h bar squared, uh, you plug in these values, you'll have these terms appearing, not surprising when you consider these terms. And for the case of the singlet state, well, this will be equal to 0. And then you'll have minus 3, 4, minus 2, 4. So that's why you have minus 3 halves. And then, well, so some simple algebra will give you um, this result for the triplet and the other for the singlet. But, well, there's a difference, right? So, um, well, we consider something else in a second. But basically, uh, the first point is that the spin degeneracy of the ground state is removed in this correction, in this hyperfine correction, due to the effect of spin-spin coupling. And so if you notice, the energy correction in this case is positive in the triplet case and negative in the singlet case. So for the triplet case where the spins are parallel, the energy increases, and in the singlet it decreases. And moreover, if you were to consider transitions between the singlet state and the triplet state, so there would be an energy gap when jumping from one across the other. And this gap, if you call it delta E, is basically obtained by the difference, where you have minus minus is a plus. So you add it and you'll have this formula, right? So, I mean, introducing a 3, both numerator and denominator, you'll have the 4/3 appearing over here. And this is of the order of 10 to the minus 6 electron volts. Now, when you have jumps of this type, of course, there is some energy in the form of an electromagnetic wave emitted. And if you use the, well, Planck's law to calculate the frequency of the photon, in this case, and so basically first we'll calculate the angular frequency and then the frequency and then the wavelength. So this comes from, okay, the Planck's law, nu equal to delta E divided by h. So this is going to be 1,420 megahertz. And then if you want to calculate the wavelength, this is basically c over nu, which is 21 centimeters. So the reason I give you these numbers is because on one hand, this wavelength is in the microwave region. And on the other, this wavelength is one of the, or this wave is one of the most common radiation forms in the universe. So, I mean, this phenomenon is happening basically outside planet Earth, right? But in any case, I mean, as a way to summarize the material, so we have introduced additional effects in the hydrogen atom, where we have a hierarchy of corrections to the Bohr energies. The first one is the fine structure, which is due to the relativistic corrections to the kinetic energy and the spin-orbit coupling, and higher order correction beyond the fine energies, the hyperfine, which is related to spin-spin interactions. So, this is a short topic. I think it just tries to exemplify the use or how useful the time-independent perturbation theory can be to analyze real-world problems such as the hydrogen atom. And these variations, such as the fine structure and the hyperfine energy corrections, they appear spectroscopically. So they have a really impact into basically accounting for experimental observations. So I again encourage you to look for the fine structure diagram of energies in the Griffiths book, which is not to scale, but it's quite illustrative of what's going on, and review the material in the references that I give you. But yeah, for the purposes of the course, this is a short topic for exemplification, and we'll continue in next lecture with time-dependent perturbation theory. So good luck with the homework. Again, I'm available through office hours, and I hope you are safe and healthy after the crazy week in Texas due to the weather. So best of luck, guys.